we already discussed about the Kirchhoff rules, then Western bridge also. So Western's bridge can be used for finding the unknown resistance. So in that one we have to use three non resistors and one unknown resistors. So there is a device which is based on this Western's bridge, or we can say it is using the principle of balanced Western's bridge. So that device is called as meter bridge. It is called as meter bridge because its main part is a 1 meter long uniform resistance wire. That is the main part of that. So its length is 1 meter. That's why it's called as meter bridge. So meter bridge uses the principle of Western's bridge to find the unknown resistance. A meter bridge consists of a 1 meter resistance wire. Generally, this resistance wire will be something like a nichrome wire. This is the main part of the meter bridge, and this is connected with some thick metal strips, generally thick copper strip. So this is a thick strip. So there can be question can come, why we are using a thick strip there. It's very simple. When the strip is very thick, the resistance will be very small or negligible. So this entire setup is in a wooden plane. So you have a wooden background. On that one we have thick metal strips like this, and we have a wire which is a nichrome wire or a resistance wire of 1 meter, and below this one you will have a scale, meter scale. 1 meter will be marked in that one. You will have a meter scale also here. Now here this much is the main part of the meter bridge, and this meter bridge, to work this meter bridge we have to connect a driving cell for this one. This is the power source for this one. You can go for a key also for this one. So generally a 2 volt or something like that can be given to this one. So this is one part. Now here we have two resistance. So one resistance is the non-resistance, that is a resistance box, and another resistance is unknown resistance. So one we will write as R and another we will write as S. So out of this R and S, this R is the unknown resistance and S is the non-resistance. It can be opposite also, but the equation will change according to that one. Now from the center point we have to take another connection like this, and in that one we have to connect a galvanometer here, and from this galvanometer, the wire which is coming, we will use a jockey here. Jockey means it will be something like a pen which we can slide over the wire like this, so we can touch at different points. So from this edge, which point we are touching, that we can find out. For example, this jockey is touching at a distance L from this edge. So you know this total, it is 1 meter. So if it is from this edge, if it is touching at a length L, the remaining this length will be 100 minus L. Okay, now this setup, when you move like this, when the jockey we are moving here, this galvanometer will show different values, and what we have to do is just like what we discussed in the Western's bridge, we have to go for a null deflection. Null deflection means this value should be 0. That is, this galvanometer should show 0. That is called as the balancing point. So if you move here at a particular point, you will get the balancing point. Now you see here, this can be compared with our Western's bridge. So Western's bridge had 4 resistance. If you remember, Western's bridge had 4 resistance like this, and you have a cell also like this. In this diagram you see here, I am marking some ABCD like that. So let this point be A, here B, here it is C. Okay, then here our E is there. Now the same thing if you compare, you see here, this is A. So from A to the B we have a resistance. Here also same thing, R. And this point is our B. From B again another resistance S, it is coming here to C. Now in between here we have a galvanometer. That is the same as this galvanometer which is coming here to this point. And here we can see, here we have a, this L wire is there. Here 100 minus L is there. So this L is the length of the wire. So if the wire is having a resistance of RCM, means resistance per centimeter, into L, that will be the resistance of this much wire. That is, the wire from here to here is having a length of L, and per centimeter, if the length, the resistance is RCM or R, then R into L or RCM into L will be the resistance of this part. Then remaining this part will be 100 minus L into RCM. So these two are almost similar. So here we have, like, so here what we have, the equation R minus this one by this one is this one by this one. So how it will come? R by L is equal to S by, okay, I will write it so it will be more clear. So once more I am telling, here the resistance of this part, or in this diagram, this part, that is R, divided by resistance of this one, that is L, length into RCM, that is per centimeter, if the resistance is RCM, that one into length L. This is equal to this side, S divided by 100 minus L into RCM. So this simple RCM you can cut there. So R by L is equal to S by 100 minus L. Now already we discussed in this equation, our unknown resistance is R. So how we can take R is equal to S into L divided by 100 minus L. So this is a simple relation for our unknown resistance. So once more we will go back. So this is the setup for a meter bridge. Here we have a uniform wire. So this wire should be uniform, and here we have two resistance. So this is the unknown resistance which we have to find out. This will be a known resistance. It will be a resistance box where we can put different values of resistance. Now what we have to do is, you put a particular value here, then you connect like this. You have a galvanometer also here. You touch this galvanometer's wire with the help of a jockey to this wire, and you slide here. Actually you should not slide, you have to take and keep at different points, because if you slide, the wire will get damaged. It should be a uniform wire. So you take and touch at different points. So you will get, for particular point, you can see that it will show null deflection, or it will show a reading of 0. So when the 0 reading comes, what is the meaning of that one? This is balanced condition. Comparing with the Wheatstone's bridge, what we can say here, this resistance by this one is equal to this one by this one. If you compare with this Wheatstone's bridge, write the equation. Here resistance is R, and here if resistance per centimeter of the wire is RCM, then R by L into RCM is equal to S by 100 minus L into RCM. Now this RCM you can cancel, then you can write R by L is equal to S by 100 minus L, or R is equal to S into L by 100 minus L. So this is the final result. Using this relation, you can find out what is this resistance. Now you see here, if you put one value of S, you will get one balancing point. If you change this one, you will get, so for example, this is a resistance which is coming almost 10 ohm. You don't know how much it is. So here you can go, if both are 10 ohm, this balancing point will come at 50. You can change here 11 ohm, 8 ohm, 7 ohm, then 12 ohm, 15 ohm, different values. Then we can take the average of that one. This will give the best result when the balancing point is somewhere in the center. So this and this one, if it comparatively similar resistance, you will get best result. Its reason also you can guess, because we are taking the ratio here. When you are going to the end, the 11th standard you studied, the error will be more. The chance of error will be more in the edge. So if it is similar number, the error chance is very less. Okay, you studied the errors and all. So the relative error and all is studied. So that error will be less in the middle part. So comparatively similar resistance if you get, or you arrange it. So there is a question, how you know what is the value, how to take similar. So when you put different value, you will get different. So you select in such a way that the balancing point comes somewhere near to 50. So you will get the best result. So using this equation, you can find out the unknown resistance. So this one is our meter bridge. It works based on the principle of Wheatstone bridge or Kirchhoff rule. Kirchhoff rule is there, but generally they will ask which device works based on the principle of Wheatstone bridge. Explain its working, means you can write this one. And you have to do the same thing for practical also. If you find out the resistance, you can use it for many things. You can verify the series and parallel combination of resistors to check. You can do that one, how you are doing with the Ohm's law. And you can find out the unknown resistance, and if you want to find out the resistivity or specific resistance, for all such purpose we can use this device. Just like meter bridge, another device which is commonly used is called as potentiometer. This potentiometer consists of a long wire. It can be 4 meter or 7 meter or 10 meter long uniform wire, which is a resistance wire like nichrome wire, and this is used for different purpose. So this main purpose of that one which you are studying is for comparing the EMF. That is, you have two cells. So when you have two cells, how to compare the EMF of these two cells? So you will get the ratio of the EMF. For that one we will use this potentiometer. And simply we can think, if you take 1 voltmeter and measure the voltage of both, you can compare the EMF there also. But the difference is, when you use the voltmeter, a small current will pass through this voltmeter. So when a small current is passing, what you are measuring is the potential difference, not the EMF. Because when you are measuring the EMF, current should not flow. So this potentiometer is using this null deflection method. That is, no current is drawn during the measurement. So that's why this potentiometer is better than a normal voltmeter for measuring the or for comparing the EMF. So now we will discuss how a potentiometer can be used for measuring comparing the EMF of two cells. We call it as two primary cells. And again, the same potentiometer can be used for finding the internal resistance of the cell also. So these two are coming as a practical for you, along with the meter bridge. Meter bridge practical is there. You have 3 practicals in meter bridge, and you have two practical in this potentiometer also. Now we will go to the principle and working of the potentiometer. Now we will discuss about potentiometer. This potentiometer is a device which is used for comparing EMF and for finding the internal resistance, etc. So as I told you earlier, for potentiometer we have a long wire. So I am just drawing like this much only. Actually it will be having so many times. It will go there, come back like this, so many times it will go. So it can go up to 10 meters. So this one is just 1 meter here and 1 meter here. It will be 2 meter only, just for you to understand. It can be bigger also, up to 10 meter. Generally potentiometer will be up to 10 meter. What you have in the lab, you have 4 meter, 7 meter, 10 meter and all. So this is a resistance wire like this. Okay, generally this will be a conductor, so that here this resistance no need of considering. Now this potentiometer, we have to connect this potentiometer to a primary circuit of this one. That is, for working of this one, we need a battery and all. So for that one, what we are doing is, we will connect a cell here, and this should be little bit bigger than what we are using here. Okay, if you are discussing about the comparison of EMF, we are comparing some EMF of something like 1 volt or 1.5 volt. This should be a little bit more than that one, something like 2 volt or 3 volt. Now here we have a controlling variable resistor or rheostat. Generally we will use rheostat, and here you have a key also. Now you see here, what happens is, for example, this is having a particular EMF, for example 4 volt. Here some drop will be there across this resistor. Remaining drop will be here. So this part is called as a primary circuit. So if this is 4 volt, here some 2 volt is gone, and remaining 2 volt will be there in this line. Now this is applicable whenever we are using potentiometer. This much circuit is common for everything. Now we will think about the comparison of EMF using this one. Now before drawing the comparison circuit, now you see here, from here to here we will have some voltage, that is from V or from A to C. So this voltage can be any value. Now you see here, this I told you it can go up to 10 meter or something like that. So that length, generally we will write it as L. L is the total length of that one. Now per centimeter, the voltage that is given by phi. That is called as potential drop per unit length. That is, in this one, if you take 1 centimeter, how much is the voltage? I told you for this 10 meter we have 2 volt, for example. Then 10 meter we have to convert into centimeter. Then 2 volt by that much centimeter. That will give in 1 volt how much, 1 centimeter, how much is the volt. That is called as the potential drop per centimeter, or it is potential gradient or potential drop per centimeter. That is marked as phi. Now if you take from here to here a particular length, here to here you are taking a particular length L. So in that L length, how much will be the potential or the EMF? EMF up to that length EL will be phi into L. Just meaning is for 1 centimeter, if 0.1 volt is there, if it is 6 centimeter means it is 0.1 into 6, that much potential will be there. That just you have to remember. Now we will go to the comparison of EMF. How we can use this one for comparing the EMF. See here, we have to connect 2 cells which we have to compare here. So these are 2 cells. Now very important thing which people generally do mistake. Whenever we are connecting, this cell is having some positive. That positive is coming to this point A. This cell's positive also should come here. This cell's positive also should come here. If you are not connecting like that, one positive instead of positive, if you are taking negative, your entire circuit will go wrong. So this positive, all the 3 positives should come to the same side only. And here we have a two-way key. From the two-way key, we will take a connection to a galvanometer. Okay. And after galvanometer, a high resistance is there. This is for the protection of the galvanometer when you are doing the experiment. But generally, if you don't connect that one also, it will work. Okay. Similarly, to measure the current, we can keep a ammeter also here. All those things are not there also, it will work. But for the accurate calculation, we can go for all those things. Okay. Now, from this high resistance, we can take and you can connect to this point. So this is for the first reading, L1. Now you see here, this one will give a balancing point when you are connecting the first cell. That is, you are putting the key here so that the first cell E1 is connected. Then you will get for E1 you are getting a balancing point at L1. Similarly, you remove this one and you connect here. For E2 you will get another L2. So like that you can get 2 for this one. Okay. Now we will go to the real part of this one. So see here. Now if you apply, you consider that you connected this first one only, first cell you connected. So if you apply Kirchhoff rule for that one, so I will draw from here. From here you are starting through this way. You are coming through this way like this. This way you are coming to this way. This is your circuit. So for that loop, if you apply Kirchhoff rule, so the main drop is, one drop is in this line. So that already we discussed. That line will be phi into L1 is the drop in this one. Plus, as this is in the balanced condition, in the galvanometer there will not be any drop. So phi into L1 plus this 0 is for our galvanometer, there is no drop, minus E1 is equal to 0. So this is the equation when you are connecting this first cell. See here, if I go like this in this way or this way, that will have a small difference. That is, if this one becomes positive, this will become negative. If this one is negative, this will become positive. That is the difference. So we are taking this way. So that's why this EMF of the cell is negative here. And you are coming here and this will be positive. So the total EMF will be the total for the entire loop, it will be 0. Similarly, when you connect the second cell, you can write another equation in the same way. So that equation will be phi into L2 plus 0 minus E2 is equal to 0. So if you divide this, or if you can again write this one as phi into L1 is equal to E1, phi into L2 is equal to E2, or you can write E1 by E2 is equal to L1 by L2. That's all, very simple. So this is the way you are comparing. So if you have 2 cells, then the ratio of the cell will be the potential ratio of the EMF of the cell will be same as the ratio of the balancing point. That's all. So first, when you see this one, it will be a little bit difficult for you. You just watch these things one or two or more time, then only you will understand how it works. Now let us check how we can use this same potentiometer for finding the internal resistance of a cell. So the potentiometer circuit will be similar. You have the wire like this, and I told you this will be A and this point will be B, and you have a primary circuit with a cell here and the rheostat which is variable, and you have the battery. So same circuit here. This side you have the cell like this, and you have the galvanometer, and if you want you can go for the higher resistance and you are connecting here. Okay, now previous case what we done is we used two cells because we were comparing the two EMF of two cells. Here we are comparing the EMF and the voltage of this cell. So when you compare the first for finding EMF, it is like this, and for taking the voltage what we will do is you will keep another key here and another resistance box R here, and you will connect like this. So the purpose of this one is first we will keep this key open so that we will find the balancing point for this one, that is when no current is drawn from this cell, because we are discussing about EMF. When you are doing EMF, no current should be drawn. So the galvanometer shows 0 means here it is open, so through this wire no current will be passing. So when it is balanced, no current is passing, so that will correspond to EMF. Now if you put the key here, once if you put the key inside this one, then what will happen? A current will pass through this one. That time if you take the balancing point, that balancing point will correspond to the voltage, not the EMF, because a current is passing through the circuit. So as I told, first when this key is open, we will get a balancing point, that is E is equal to phi into L1, similar to the previous equation. Now when this key is closed here, a current will flow through this one. How much is the current we will discuss later, but you should know that there is a current through the circuit. When the current is passing through the circuit, instead of this EMF E, we have to write V. V is equal to phi into L2. Now if you take the ratio of this one, E by V is equal to L1 by L2, like that you will get. Now we have the relation between E and V, so that we can take here. What is that? E is equal to V plus IR, like that we have equation. V is equal to E minus IR, internal resistance R. Now what is this V? This V is I into R, or simply if you rearrange this one, we can write E is equal to I into R plus R, and for V we can write just V is equal to IR. This equation also we can write. So what you will get by taking both equation together, you will get E by V is equal to I into R plus R divided by I into R. This you can cancel. So E by V is equal to R plus R divided by R. So already we have here E by V is equal to L1 by L2, and here we have E by R is equal to R plus R divided by R. Now these two equations if you equate, what you will get? R plus R divided by R is equal to L1 by L2, or this internal resistance R can be written as R into L1 by L2 minus 1. So this is the internal resistance. So once more I will explain this one for you to clearly understand. In the previous case we were connecting two cells. Here we are not connecting two cells. Here we are connecting only one cell. First we are connecting this one cell, then we are finding what is the balancing point for that one. So you will get the equation E is equal to phi into L1, just similar to the previous one, that is a comparison of EMF. Then we will add this circuit also. When we add this circuit, what will happen? A current will pass through this circuit here. So this EMF will drop, this will become voltage, small drop will be there. So the balancing point also will move a little bit toward this side. So when the balancing point is moving toward this side, what will happen? You will get another equation. So that time you cannot write V, we have to write, so we cannot write E, we have to write V, because the current is drawn. Now it is not EMF, it is the potential difference. Now if you take the ratio of this one, you can write E by V is equal to L1 by L2. Now from the basic definition of the internal resistance, there we have the equation V is equal to E minus IR. Now so you can write E is equal to this you can write like this, E is equal to I into R plus R, because V is equal to IR already you know, V is equal to IR, this equation also is there. Now this one, if you take again the ratio of E by V from using this equation, you will get it like this. From this one, again if you compare with the previous equation, you will get this one, R plus R by R is equal to L1 by L2. Once more, if you write yourself, you will get it. It's a very simple thing. You can just take the textbook. If you know the working, it's a very simple thing. So you can get the internal resistance using our potentiometer. So this is a very, very important topic, that is Western bridge, then meter bridge, and these two uses of the potentiometer. All these are very, very important. Mostly it is coming for a 3 mark or 5 mark question every year. So you should be very much clear about that one. You can go through this one many times, 4 times, 5 times, so that you will understand it clearly. And there will be so many higher level questions from this one. To answer the higher level, first this much basic thing you should know. So first you study this much basic thing, then later we will go to the higher level idea about this one, the problems based on this one, and some other application level questions, everything we will do after that. Thank you.